All right, guys. So for video assessment number 1A, the question asks us to draw a position versus time, a velocity versus time, and acceleration versus time plots, and fill them out by using the provided velocity versus time curve. So we already have basically the velocity versus time chart. How can we fill out the position graph and the acceleration graph? Just by using the velocity. And it's actually pretty simple. There's multiple ways to do it. What I find easiest though is by using a little bit of calculus and graphical analysis. And so, um, what's interesting is that velocity is actually just the derivative of position, and similarly, acceleration is just a derivative of velocity. So we can say that since velocity is a derivative of position, simultaneously, position is just the integral of velocity. And so when we take the integral of velocity, we can just find the area under the curve. So what I have here is the area of a square and the area of a triangle. I split up the curve into two shapes, and we have that the area of a square is just the length times width. So we see it has traveled 4 seconds, or 4 meters, sorry, and 2 seconds. So we multiply 4 times 2 equals 8. We can jot that down on our position graph. We traveled 8 meters in 2 seconds. And then we can look at the next portion of the velocity graph, which is a triangle. And so we'll be doing 1/2 times base times the height. And we get that is 4 times 2 divided by 2. And we get that it is 2. So within the next 2 seconds, we only travel 2 meters on our graph. And when we add it up, we get a total change of 10 meters in position. Now, simultaneously, we can do the same thing for acceleration. Instead of taking the integral, we'll be taking the derivative of the velocity curve. Now, not only can we do this whole calculus trick, but we can also solve it through kinematics. I'll quickly show it through kinematics here. By taking this equation, final velocity is equal to initial velocity plus acceleration times time. We can manipulate it to where we isolate acceleration, and that is equal to the final velocity minus initial velocity divided by time. So when we fill that out, we know that our final velocity is going to be 0 because of the graph that's supplied. And we know that our initial velocity is wherever we started on the graph as we decelerated. So that's going to be at 2 seconds. And at 2 seconds, we traveled at 4 meters per second. So we have 0 minus 4 meters per second divided by 2, because within that interval, it was 2 seconds. And we find that A is equal to negative 2 meters per second. And so that's how we filled out our acceleration graph right here. Now, we can also do the calculus / graphical analysis method too, which is just basically if we want to find the derivative is the slope of a curve. So we can look at our velocity graph and we can say that slope of velocity at 2 to 4 seconds would be 4, 2, and write it this way. So we'll have that acceleration is equal to the derivative of velocity in relation to time, which is just going to be rise over run. So that'll be 4 over 2. And we get 2. And since it's decelerating, we're just going to stick a negative there. And it's the same thing as our kinematics equation. So this was a pretty interesting problem because it highlights both or two ways to solve it. Obviously we can do the kinematics way, which is probably more in line with what we learned in class. Although I think it's pretty interesting to note this other calculus / graphical way, and also kind of highlights the relationship between position, velocity, and acceleration. It already builds upon what we know through the kinematics realm. And if we were to just apply this to some like physical model, we could probably say it was some skateboarder, traveling at a constant velocity, 4 meters per second. And he just decided he wanted to stop. Maybe he's trying to cross the street and there's some cars. And so he skids to a stop with a deceleration of 2 meters per second for like a total distance of 10 meters from wherever he started from. Anyways, guys, that's video assessment number 1A. Thank you.